The second half of section 3.2, specifically focusing on is a linear model a good model for an association? So we have worked with these things in a previous video, and we're now going to look mostly at residual plots and R and S to tell you how strong of a model it is. And then in the last video from this, we're going to talk about regression wisdom, just the things that we know about least squares regression lines and what we can do. But that'll be the last video of this unit. So a residual, as we talked about, is the difference between the model's prediction, this once again is the model, and then the actual data from which the model was given. And a residual is written in symbols, y being the actual data point and y hat being the prediction from the model. That's a residual. So we can also call the residual an error of the model, and that'll help us to understand some of the other stuff later. It's actual data, so it's not an error, but it's if you're talking about the quality of the model, then each residual is an error from the prediction. Hiya. So one of the things we're looking for when we're trying to decide if a linear association, a model of using a regression line is a good idea, one of the things we do is to check to see if there's any lurking patterns that we can't see. So we make a residual plot, and the residual plot basically says we're going to go ahead and take the x value of our original xy points, and instead of y being the output, we're going to go ahead, or the response variable, we're going to have y as the residual at x. So when we plot those, we're going to find out that in this case, there's no pattern whatsoever. And if there is no pattern whatsoever, then we can use the linear regression line or model to help us. If there's some lurking pattern, then we find out that perhaps it may look like a linear association, but it's something else altogether. So what we're looking for is in our residual plot, we're looking for a totally scattered pattern with no lingering patterns in there. So a reminder that residuals are they are a way of talking about the error in the model. So by plotting the input and the error, the residual, you can see if there's any lingering patterns that would make the explanation of what's happening in terms of that error, that residual between the prediction and the actual data point. We shouldn't see any patterns. So if we did a residual plot and we found this parabolic pattern, or if we did a residual plot and we found this curve, we would say for sure that we should not use a linear model or a linear regression line to analyze that data. So we should see no obvious patterns, and the residual should be relatively small in size. So keep in mind, like the Ford problem, a residual of 5,000 might be perfectly appropriate, but with the inches for a long jump, then the residual 2 or 3 might be appropriate, but if we had a residual of 25, that might be way up. So that's what it means by relatively small in size. It's got to be relative to the situation and the context that you're dealing with. So once we've decided that a linear regression model is appropriate, we also want to look to see how strong of a model the one that we have is. And keep in mind, we're going to choose the least squares regression line as the best, the ideal model, but still it may not have that much a really strong predictive quality. So the way we're going to measure that predictive quality is to see how far off their errors are from the original, the standard deviation of the residuals. So we're going to calculate this S value the same way we've calculated standard deviation in the past. So we're going to take each of these residuals and we're going to square it. We're going to add them all together. We're going to divide by n minus 2 this time and then take the square root. So we're going to take, once again, the original value minus the predictive value and square those, add them all up, and divide by n minus 2, and then take the square root. And that's your average typical prediction error. And so S needs to be interpreted in context for us to understand if it's strong or not.
The second measure of how strong a linear regression model is in terms of its predictive power is R squared. And we don't really need to pay much attention to the formula, but we do need to pay attention to some qualities of the formula. For one, R squared has no units, whereas S has units that relate to the response variable, or the Y. R is just a measure of percentage. And so R squared tells you how much better the least squares regression line does at predicting values instead of just simply guessing based on the data itself. So this particular collection of words you're going to need to copy down and use it as your sentence stem whenever you're talking about the R squared. Because it makes sure that you cover all of the things that the stats test requires of you. So you're going to basically plug into the little parts of this about R squared, and you're going to take the decimal form of it and put it into the percent form about R squared percent of the variation, and this is going to be whatever the Y is, and this is going to be whatever X is to Y, and we'll talk about that in an example in just. So we're going to put all this information together, interpreting the least squares regression line, calculating a residual, looking to see if it's a valid model by looking at the residual plot, and then also talking about what S and R squared tell you. So this is 12 college football teams, and we're looking at the relationship to points per game and wins, and obviously there's a fairly strong linear correlation. And before we move to the next slide, because it's even talk about it, I want to make sure that you slow down whenever you're given a least squares regression line and just figure out what each of the pieces means. And in this case, the change in Y has to do with the number of wins. So you're going to expect 0.437 wins for every 1 point extra scored. Spend the time to understand what's happening. The y-intercept doesn't actually mean anything in terms of the data itself, but it is where the 0 points would be. Calculating residual is just plugging in the x into the equation to find the predicted value. Remember, the predicted value is y hat. And then we're going to take the actual data point at that x value and subtract the predicted value to give the residual. And this is, remember, the residual is the difference between what's predicted, which is the y hat, and what actually happens, which is the y. And we can call that the error of the model as well. So when we are looking about the appropriateness of a linear model, we're going to look at the residual plot. And we're going to look at strength of a linear model. Strength is here. And strength is here. We're going to look at both the R squared and the S. So these are strength, and this is appropriateness. Just like when we looked at decided whether a normal distribution would be appropriate for a set of data, and we looked at a normal probability plot. We were looking for a pretty straight line without any curves or outliers. We look at a residual plot to decide if a linear model is appropriate for comparing an explanatory and a response variable. And these residual plots, we are looking for no pattern in the dots. And so this is all scattered. We can assume that for this particular situation where we're comparing points per game to wins, we can use a linear model. And so the linear model we have has an S of 1.24. Notice that 1.24 does have units. It talks about the wins, which is the y value. It says the least squares regression line that we have, where x is points per game and y is number of wins, will typically be off using that least squares regression line by about 1.24 wins. Keep in mind that we, unlike R, where we're like, okay, perfect correlation, negative correlation, perfect correlation, positive correlation, something in between, zero is no connection at all. We can't do the same thing with S and just say a low number is better, or because this from 1.24 games off sounds kind of good. We're going to look at a model, one in the couple of slides where it's about car cost, and so if it's off by 1,000 or two, that might be an actually strong model, even though it sounds like a really high number. Whereas R squared, the closer you get to 100%, it's obviously a really, really strong predictive model. And once again, I'd like you to make sure that you're familiar with, and you go ahead and use this this sentence frame where you're just plugging in information. You're plugging in this, 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 and this when you do it. So you're going to say about 88% of the variation in wins, in this case, because wins is the y, is accounted for by the linear model relating wins to points per game. And you can do points per game to wins, it doesn't matter. But it's the fact that you have the percent in there, the variation, the accounted for by the model, and then the wins points per game. So just write that down, memorize it, and be able to plug in the stuff that you need. So looking at the computer regression output, you need to be able to recognize the information and find the y-intercept, which has been labeled for you. So you could start writing your least squares regression line. Here's your y-intercept, and then your slope. And you can write that as miles driven instead of x if you'd like. That's very common in a regression line. So instead of writing a variable, it actually talks what that variable is. We could then use that to calculate residuals given a particular data point. And we can also talk about the S and the R squared. Obviously, they decided they must have already looked at a residual plot to decide if it was an appropriate model. But once they did, their S means that the typical resale cost is $5,740 off. That's the typical error. So the typical residual is about $5,740, and about 66% of the variability in resale value can be attributed to the linear model, comparing miles driven to resale value. So this particular video talks mostly about these two things, and then R squared and S. The last video we'll kind of bring it all together, where we talk about how to calculate the least squares regression line using with a calculator, and then also just how affected least squares regression lines and such are affected by outliers. So that'll be the last piece